Hi Algebra 2 students, how you doing today? We're doing the last section of chapter 7. It is section 7.8. If you notice, we skipped 7.7. We did not need to do that section on transformations. Today we're going to do curve fitting with exponential and logarithmic models. Models are equations, so what we're going to be doing is we're going to have sets of data, and we are going to be using our calculator to ask it to write exponential and logarithmic equations that match the data. That way we can use it to analyze the data and make predictions about the future. So today the biggest part is, can you find how to do this on your calculator? So if you're watching this video, pay really close attention to the buttons on the calculator. So we are going to model data using exponential and log functions and use to analyze and predict. We're going to do exponential regressions. That's using data to find an exponential model or equation. And we are going to also take a look at whether data is linear or exponential. I'll show you how to do that. We're going to do a logarithmic regression. So we are going to use data to find a log model. Your calculator has both of these features on it. So key concepts when you look below: a regression is a model or an equation. So for an exponential equation, when you see here on the left, we know what that looks like. That's f of x equals a times b to the x. And that is the EXP-REG on your calculator. We'll show you how to find it. And an exponential model shows, to get from one output to the next, you'll see that you're multiplying by a constant to get from one value to the next, and that is, of course, the base. We knew that. The base is what you're multiplying by. You haven't seen a logarithmic regression on your calculator before. That is f of x equals a plus b times the natural log of x, and that's an LN, natural log regression, on the calculator. We'll show you how to find that too. At the bottom here, number 4 is actually going to be the last problem that we're going to do. So we are going to turn the page. And on the first page, we're first going to be looking at comparing exponential, not logarithmic, just exponential models to linear models that you're used to. If you remember with a line, when x changes constantly, the y changes constantly also by adding or subtracting. And that is not true with exponential. Exponential involves multiplication. So we are going to check to see if a set of data is linear or exponential by what we know. So first of all, when you're looking at a set of data, you have to check to make sure that the x values are increasing constantly. And notice in our data sets, they're each going up by 1. Not that they have to go up by 1, but they just have to go up constantly. By doing this, we can then take a good look at the y's. If the x's weren't changing constantly, then we really wouldn't be able to tell well what the y's are doing. So we first check those x's. The next thing we do is we find the successive difference of the y values. In other words, we take a y value and subtract the y value before. We take a y value, subtract the y value before. Take a y value, subtract a y value before. And those are called the first differences. And we're going to use those to see if a data set is linear or exponential. Another thing you could do is actually graph the data points that are given to you in the table. Right here's -1, 2.2, 0, 3, 1, 7, 227. You could graph these points and see if they form a line, or you can graph them and see if they form a curve that's exponential. So notice on this first set of data, they took a y, 3, and subtracted 2.2 and wrote the difference underneath. That's 0.8. They did 7 minus 3 is 4, 27 minus 7 is 20, and so on. If you notice, these y2 minus y1s are not constant. That means that this set of data is not linear. If it was linear, these changes in the y's would be constant. It would be the slope. So the next thing we're going to do is check the ratios of the first differences. Okay, so here's our first differences. 0.8, 4, 20, and 100. And what you do is you take the second difference divided by the first difference, and you go down the row. So here we go. 0.8, 4, 20, and 100. So we're going to take a second difference divided by the first difference. 4 divided by 0.8 is 5. Next, 20 divided by 4. 20 divided by 4 is 5. There we go. Next, 100 divided by 20 is 5. Or if you look at it another way, notice if you multiply 0.8 by 5, you get 4. 4 by 5, you get 20. 20 by 5, you get 100. That's multiplication of a constant, and that is exponential. There we go. Let's check the next data set. Here's our x's are going up constantly. Here are our y's. They did y2 minus y1, y2 minus y1, all the way down the row, and they got that those first differences are all 3. Meaning that this is a linear set of data, and if you graphed the points, you would see that they form a line. Okay, let's take a look at the bottom here, and let's see if the data sets are exponential or linear. So let's first find the first differences. So let's take a look at the x's. They do go up constantly. They already did 2 of the first differences for us. 1.5 minus 0.375 is the 1.125. There's the first difference they have. The next difference, 6 minus 1.5 is 4.5. The next difference, 25 minus 6 is 18. There we go. And 96 minus 24, the last difference, I believe is 72. It is. So obviously these first differences are not constant, so they're not linear. Let's check the ratios. We're going to take a second difference divided by the first difference. 4.5 divided by 1.125. Let's find out what that is. 4.5 divided by 1.125. That is a 4. Next, 18 divided by 4.5. Second difference divided by the difference before it. I feel like that's going to be a 4. It is. And last, 72 divided by 18. The last difference divided by the difference before it. That is also a 4. So because the ratios, a ratio is a fraction, by the way, are all the same, this is exponential. Let's check out data set number 2. The x's are going up by 1 constantly. Let's find the first differences of the y's. y2 minus y1. 6 minus 3 is 3. 9 minus 6 is 3. 12 minus 9 is 3. 15 minus 12 is 3. Because the differences are constant, this is linear. We do not have to check the ratios. Awesome. Let's check the next page out. So there's a lot going on this page, so you kind of have to pay close attention because they first ask you to put data into a calculator, and on the left, we have to get the calculator ready for that. See if you can see that a little bit better. Then we're going to ask the calculator to do some calculations for us, and then we're to get a regression equation, and then we're going to graph it and use it. So we have a lot going on here. What we're first going to do on the left to get our calculator ready, right? So we're going to write, this is what we're going to do to get our calculator ready. We are going to hit our y equals and make sure there's nothing there. Let's clear that out. Now, next, you probably haven't heard of this before. When you look on your paper, right where I'm circling, there is an r squared and an r. We are going to be looking at this r squared, and for us to do that, we need our diagnostics on, and this is how we do it. You only need to do it once when you turn the calculator on, and then it's good for the time that you're using it. So here we go. To turn diagnostics on, we are going to use second 0. So look above the 0 button, it says catalog. So we're going to do second 0. And this is where we find diagnostics on. So we are going to scroll down to the D's. Notice the catalog is in alphabetical order. Just looking for diagnostic, there's off. Let's turn diagnostics on. And then you enter. This way, when we ask our calculator for an equation, we will be able to see the R squared. Without the diagnostics on, we won't be able to see it. Okay, the next thing we need to do is we need to tell our calculator what we see on the paper. We are going to make 2 lists on our calculator, and we're going to put this data into it. And here's how we do that. We are doing statistics. Let's move this over a little bit so you can see it. So we are going to hit our statistics button, which is just to the left of the cursor keys. And we want to edit, right? We want to edit and let the calculator know what data we have in the table. Now what I'm going to do is I'm going to show you how to clear data from L1, list 1 and list 2, so you can input data. So it's written here, you clear data by highlighting L1 or L2 and press the clear button and then down, which kind of makes sense. So highlight L1 and then hit clear, which is right beneath the cursor keys and down, and it clears everything that's down. Let's go over to L2 and let's hit clear and down. And now what we're going to do is put in our L1 the time and the bacteria in L2. So time always goes in L1. So to get each piece of data in, right, I'm going to start with a time of 0. You can cursor down or hit enter. I'm going to hit enter. So there's 0, 1, enter, 2, enter, 3, 4, and 5. The next thing I'm going to do, go back up, fill in my bacteria list, 120, enter, 205, enter, 369, enter, 640, 1132, 1972. I do suggest at this time that you just take a moment and look at the data that you entered rather than going ahead and making mistakes later. Just check and make sure that you didn't make any mistakes when you were entering the data, because it's really easy to do. Okay, so now our calculator knows what's on our paper. And we said, let's see, it's asking for an exponential regression equation. So that data that we need is right here, that information. We're going to hit Stat and Calc and look for exponential regression. So here we go. Again, we are using Stat because these are statistics and we want to do some calculations. So here we go. That Stat button right here again. Scooch 1 to the right for Calc. Let's look for exponential regression because they told us to use that. Hit enter. And now basically what you do, half the calculators kind of look like my screen, and then half won't have all this and you'll just kind of see a blank. That's okay. Pretty much you just hit enter until the calculator gives you your exponential equation. So I'm going to hit enter until it calculates. If your screen is more blank than mine, you just hit enter until it gives you this information. So when you take a look here, here's an exponential equation, a times b raised to the x, and the calculator is telling you what a is. We're going to write that to the third place. What b is, we're going to write that to the third place. Now, the r squared and the r you do not need to write, and what you just need is the r squared. I just want you to know that the closer r is to 1, the better your equation fits your data. Notice we have a 0.9999. That is super close to 1, meaning that our equation is really, really good for the data we put in. So the next thing we're going to do is actually write the equation with a and b in it. So let's take a look. Notice that they did on the paper here. However, I think we should go to the third place. let's see, they went to the first place, and that's going to throw us off a little bit. So I'm going to come on up over here and write the equation on a y1. We're going to put our A is 118.903. Here we go. Our B is 1.754 to the x power. There we go. This is what we're going to be putting in the calculator on a y equals now to look at it. Okay, so step 1, enter the data. Step 2, get the equation from the calculator. Step 3, let's graph it. Let's put this information on a y1. So here we go. On a y1, 118.903 and times 1.754 raised to the x. Now, we could spend time with the window, making our own window, but I think what might work best is most of the time this works really well. We're going to hit zoom and fit. So you're going to hit zoom in the middle of your calculator, right? But rather than standard, we're going to go down to fit. That is 0. And the calculator does a pretty good job, let's hit enter, of making a window that matches your data. Now there's one more thing you need to know, right? There's a lot going on here on the calculator, and let's take a look at what that is. Once we write the equation and graph it, they are going to ask us a question so we can use the information. So notice it says at the top, the data in the table below can be modeled by this exponential function. When will the number of bacteria reach 3,700? Okay. Notice what we had put into our table was our time in an L1. Those are our x's. And the bacteria is the output in a y2, right? So in our y. So they just gave us that y is 3,700, and they want to know what time that happens. Okay. Now, what we've done in the past is hit trace and gone to a y of 3,700. So I could do that. I could trace along to 3,700. But what I want you to know is we're a little better at this. That is not that accurate anymore. What we want to do is go to exactly where y is 3,700. So take a look here in the directions on how you do that. We entered in a y1 our equation, and what we're going to do is we are going to enter 3,700 in a y2. It is a y that they gave us. We already have y1 filled in, and so on y2 we're going to put 3,700. So let's go ahead on a y2 and let's put 3,700. And now I'm going to do zoom fit again so all the data fits on. So let's do zoom and let's do fit, and let's see how well it works for us. Here's zoom fit. It's thinking up in the corner here. Okay, it didn't do that good of a job for us. We certainly gave it a try. So here's what we're going to do. We're going to try the window, and we're going to make the window ourselves. So notice that the x's were from 0 to 5, but we want to go to 3,700. So let's make our time 10 and see how that works. So our x minimum is 0. Our time, instead of 5, because it's only going up to 1,972, let's try 10. Let's put in 10. There we go. Let's keep our scale 1. Now for our y minimum, it shows bacteria of 120, right? And we know we have a starting amount in our equation of 118. But you know, let's start at 0, because it is possible in the real world to have 0 bacteria. Now, it shows a y maximum of 3,700, right? That's what they're asking us to look for. But you know, let's go past that so that our information isn't right at the top of the screen. And now let's hit graph and see how we did. Here's our exponential function. And there's our line, y equals 3,700. So right at this intersection point here is the time where there's 3,700 bacteria exactly. So how do we get there? That's an intersection point. Instead of tracing, here's our trace button, we're gonna hit second trace. Okay, so let's take a look and see if they put that on here. Use the intersection feature. Okay, that is second and trace. There we go. So second trace, and let's pick number 5, intersect. There we go. Now it says first curve, and all you really have to do is hit enter 3 times. Let's get a little bit closer to the intersection point though. It's really nice to be closer to it. So close to point, and enter 3 times. I just realized I have that written over here. Second trace, number 5 intersect, enter 3 times for intersection point. More accurate than tracing. I don't know why I didn't notice that before. So, got close to the intersection point, enter, enter, enter. Notice it went right to a y of 3,700, and it tells you that that happened at 6.118 minutes. There we go. Okay, let's try the problem below that we have here. Use exponential regression to find a function that models the data. Okay, let's see if I put this at the top. I'll just have to keep moving it a little bit. Okay, let's get the calculator ready. Let's clear our y equals out. Good, we cleared that out. All right, we don't have to do diagnostics on, we already did. Okay, let's put the data in the calculator. That is stat, edit. Let's clear out our L1. So highlight L1, clear down. Highlight L2, clear down. Let's put in our data. Our time is 0 through 5. 0, 1, 2, 3, 4, and 5. There we go. Again, we're working with bacteria. I'm going to put that in. That's 250, 360, 485, 686, 964, and 1,348. Let's give a quick check. Make sure we put the data in correctly. We did. Excellent. Now we want an equation from our calculator. That is stat. We want to do calculations. I moved 1 to the right, down to exponential. There it is. I'm going to hit enter until it gives me an equation. There it is. I am going to write my A to the third place, 251.914. My base of B is 1.398. And that is to the x power. There we go, we wrote the equation here. When will the number of bacteria reach 1,800? Let's put this equation in our calculator on a y1, 251.914 times 1.398 raised to the x power. There we go. Let's also, on a y2, put the 1,800, because that's a y value. All right, let's make our own window since ZoomFit didn't work that well. A window. Let's see, my bacteria could be 0. Let's see, my X max, my chart goes up to 5, I'll double it to 10. My bacteria, the minimum bacteria could be 0. And let's see, they're asking for us to look at bacteria up to 1,800. How about if we do 2,000? There we go. Let's hit graph. There's our exponential equation. Here's our y line of 1,800. So we want to go exactly to this intersection point. Instead of tracing, do second trace, pick number 5, intersect. Let's get a little bit closer to that intersection point and hit enter 3 times. Enter, enter, enter. Notice it went right to a Y of 1800, and that time is at 5.869 minutes. Excellent. Okay, let's go back to the front page because they want you to do logarithmic regressions, and yet in your book, and yet they didn't have you do that in these notes. So of course we need to do that. We are going to do almost everything the same. Ready? Let's clear out your y equals. There we go. We are going to enter the data we see in the table. So that's stat and edit. Let's clear our L1, highlight, clear down, highlight, clear down. Let's put in our time in an L1. It goes 1 through 8. 1. Excellent. Let's go back to our L2. And apparently this is, instead of bacteria, we have speed, miles per hour. So 10, 11.4, 12.2, 12.8, 13.2, 13.6, 13.9, and 14.2 miles per hour. Let's do a quick check. Make sure we put the data in right. Just taking a good look here. There we go. Let me check my first 2 pieces of data. Looks good. Okay, now we want the calculator to write an equation for us. Notice this time we want logarithmic regression. We are still going to do stat and calc, but this time we're looking for ln. Not LIN, but ln. That is number 9 on a stat calc. All right. We are going to choose that and just hit enter until the calculator gives you an equation. There we go. Notice our r squared is really, really close to 1, meaning that this equation fits the data really, really well. So let's take a look here. Let's fill in the equation. Notice that it's a plus b times the natural log of x. So I will write that. Let's come on up here so we have some room. Y, we're going to put that on y1 equals 9.999, but we have to round it, so that is 10, plus our b, 2.009, natural log of x. There we go. Now they want us to use this equation to find when the speed is 17 miles per hour. Notice that that was on our L2 list. That is a Y2. So on the calculator, on a Y1, let's put in 10 plus 2.009. Hit that natural log button, you know where it is, X. On a Y2, let's put 17. Excellent, because that is a Y that they gave us. All right, let's make our own window. Let's see, our X minimum, let's start at 0. Our X max, let's see, our time goes to 8. We could double it at 16. Let's make it 20. Our speed could be 0. Right now, we are looking for a speed of 17. So let's go to 20 on our speed. So Y minimum 0, speed of 20. There we go. Let's hit graph. Let's see how it looks. There's our natural log function. There's the intersection point. It went off the screen, so our X max to the right, we're going to have to make a little bit bigger. So let's go to our window, X max. Let's double that to 40, and let's see if we can see an intersection point now. There we go. There we go. So it intersects over here, right? So let's find out where that is. So remember, instead of trace, second trace, and intersect. Here we go. Let's get a little closer to the intersection point and hit enter, enter, enter. 1, 2, and 3. And the calculator tells us that we are going 17 miles an hour at 32.600 hours. So 32.600 hours. There we go. So I hope you got the hang of how to use a calculator to ask it to write equations for you, and I hope you have a wonderful day. Bye.